Okay, so all of you can see my PowerPoint slide, right? Can you see something on your screen?
Yes, sir.
Yeah.
Okay, yep. So today we're going to sum up or summarize what is hydrostatic force. So again, hydrostatic force is something, a force acting on a plate or surface under water. Yeah. So again, the fundamental equation is you convert pressure equal to force divided by area. So in this case, we are interested in finding the force. So you rewrite the equation, F equal to P times A, pressure times area. Then you do the integration. Then from there, we recall what is pressure. So pressure inside the water, we need to add the atmospheric pressure or ambient pressure, P0, plus the hydrostatic pressure, which is rho GH. Yeah. So first equation is F equal to PA, pressure times area, and then you recall what is pressure. Pressure is uh, ambient pressure plus the hydrostatic pressure, rho GH. So sometimes you consider ambient pressure, sometimes you don't need. Yeah. So we have a few equations to go through. And then we already covered how to find the location of your resultant force. Yeah, so means y prime and x prime. And then we have two equation that we can use. So like what you see on the screen is y prime yc plus rho g sine second moment of your object divided by your resultant force. So the first equation that you see on the screen is when you want to include the ambient pressure. If you don't want to, if your case that you ignore the ambient pressure, then you use the second equation that you see on the screen here. Okay. Yeah. Same with the x prime coordinate. So we have also have two. So one by considering your ambient pressure, one is without considering. Yeah. And then we have already covered one example on hydrostatic force on a hinge on a plate. And last week we already covered this one. So today we're going to look at another example. Okay. All right. Now this example will be the same as your hands out tutorial chapter 2. It will be same with question number 18, 1-8. Yeah? So today we're going to look at a scenario. So let's say we have a tank, and this tank we have a door, and the door size will be 3 meter times 2 meter, and we have a hinge over here, right? So the door shown in the side of the tank is hinged along its bottom edge. So its bottom edge, which is this one is a hinge. So you know that when you hinge, the door will open like this, yeah, open like this. So we need to make sure that we have sufficient force to close this door. So that's why we have a FT here, right? FT here to make sure that the door do not open. The pressure of 100 Pascal is applied to the fluid free surface. So there is a pressure acting on the liquid here. So, and then the specific weight of the water is given, yeah. So specific weight, you have to recall what is specific weight is rho g, yeah. So specific weight is given to you already, given by 9.8 kilonewton over meter cube. So we need to find our force here to keep our door closed. Again, we are this 100 Pascal is gauge, is a gauge pressure. Okay, we start solving our problem. So we need to draw our free body diagram. So in your coming test or final exam, if you see a problem or a statement or a question, you're given an object, then you when you need to find forces, you need to derive or need to draw out a free body diagram. Okay. So something like this on the screen here. Okay. So we're going to start with, let's see if I have it. Okay. So let's focus on the one that on the bottom. We focus on the second diagram on the screen here. Okay. So we start with the axis. Focus on your axis. So we develop your X, Y, and Z axis. X, Y, and Z axis. So from here later, you know how to find the forces. So we have forces in X direction, in Y direction, and Z direction. And we have the position of our hinge here. So your hinge position is here. So the whole door will open in this way. So to avoid this door open from this way, you need a force to stop it from opening. Then our H is going down in this way, is positive. Yeah. And we have a ambient pressure of 100 Pascal gauge pressure. Okay. So the second one, you draw the free body diagram. So from free body diagram, you draw the hinge. You draw the hinge. Not hinge. This is the door, and then you draw the force. This is the pressure, hydrostatic force. Maybe, yeah. This is a. Or in this diagram is pressure force. Okay. So we have two surfaces, one on the left, one on the right. And you know that as you go deeper, you will get a higher pressure. So as you go deeper, the pressure will increase. So we know that if we go deeper, we will have a non-linear pressure on the door itself. So you look at on the left hand side, we have P0, it is ambient pressure plus our atmospheric pressure acting at this point. And as we go deeper, then we will have our rho GH, our hydrostatic force. Yeah, our rho GH here. So, and then on the right hand side, you only have atmospheric pressure. And you look at atmospheric pressure component is very balanced. It's a well-distributed pressure on the left-hand side here. And then we have a force to a point force acting on the top of the door here to stop it from moving. And our area will have area in Y direction, Z direction, and so on. Okay. Then after that we transform our free body diagram. We take out all the we try to take out the repeated pressure. So in this case, atmospheric pressure was taken out because it's acting on both sides. So we don't need to consider the atmospheric pressure. Okay. Yeah. So we assume that this is opening. This is open. So the water is exposed to atmospheric pressure, and here also atmospheric pressure. Okay. Right. So we transform the third diagram into the last diagram that you see on the screen here. So on our door here, on the left hand side, we only have the gauge pressure on the top, and then as we go deeper into the water, then we will have the hydrostatic pressure acting on the surface here. So we will have our rho GH, pressure rho GH. All right. Okay, any question on the diagram that you see on the screen here? Any question you want to ask me? Good, huh?
Yeah.
Okay.
Yeah, it's fine.
Let me see. Cool. Okay, cool is here. Right, cool. When you log in, what do you hear? Which part that I'm mentioning when you join?
You mentioned the pressure.
Which pressure? There are lots of pressure.
The F atmospheric.
Oh, so when you join, I already in the third diagram, this one.
Yeah.
Okay, so next time be punctual, yeah? Yeah.
Oh, yeah.
Yeah, because everything was recorded and it's a video recorded, so your attendance will be, yeah, it will be seen by everyone.
Because just now I have a issue problem for my internet.
Okay, right. So, yep. Okay, so let's move on. So we already covered from the question itself, and then the middle one is our consideration. The third one is after we take out the atmospheric pressure. Yeah. So again, in exam, free body diagram will give you 3 to maybe 5 marks according to the complexity of the problems. So make sure you know how to convert from the scenario into free body diagram. Okay. Important is you know that there's a non-linear pressure on the left or on the surface that uh, uh, contact with the water. Okay. And if the other side you're exposed to atmospheric, then you try to look at the vessel or try to look at the container itself. If other side is having atmospheric pressure also, then you can straight away cancel out the atmospheric pressure for left and right. Okay, that is a very important concept. Yeah. Okay, let's continue. Okay. So there are two ways lah. So either you can use the middle diagram, or you can use the third diagram. Both give you the same answer. Okay. Yeah. So we'll use the third diagram because it's take out the atmospheric pressure in our calculation. You don't need to rewrite so many times our atmospheric pressure. So we look at we'll focus on the third diagram. Okay. Yeah. So once we have the free body diagram, we will convert this portion, the pressure portion, change it into force. So again, recall what is pressure. Pressure is force divided by area. You want to focus our force. So force equal to pressure times area. So we want to find our FR. Okay. And our location is, we need to find our Y prime. Right? Y prime, every time you want to find your force, which is your resultant force, it will come in pair. Yeah? It will come in pair. It will come in uh, FR. It will come in pair, X prime and Y prime. Okay. So we always go and find in hydrostatic problems or all the tutorial question, you will see that we always start with the Y prime. Then we continue with the X prime. Okay. So from here, we convert the pressure into forces. Then the one that you have on your screen now, the third one, you only have the force component, right? You don't have the mixture of pressure and forces. So a good free body diagram with forces is the one that you see on the screen here. Yeah. So in exam, don't miss up. So you can continue to give us a cleaner free body diagram at the end. Yeah. So we're going to use the governing equation. So we know that Ft, because we have a hinge here. So when you have a hinge and you have a force, So and the direction and the distance is 90 degree. So when you have something that the distance is 90 degree to the force, you will generate moment. Yeah, you generate a twisting moment, or there's a torque moment, or a torque or moment at the point A here. Okay, so it's just a reminder. So force to a point with a 90-degree length or distance, you will get a moment. So here you will get two moment here. One is from the FR, then one is from the FT. So in this time, because FT, we need to find the FT, so we focus on FT. Yeah. So governing equation, we will use FR equal to pressure gauge times area. Because why? Because the question gives us the pressure gauge here. And Y prime, we will use the YC plus the rho G sine theta I XX, or your second moment, divided by FR. And we will use another one. It is your equilibrium equation. All the moment inside at the point A here will be equal to 0. Right, so you have two moments. One is resulted from your FR, one resulted from your FT. FR will generate FR. If you twist along A, you'll get anti-clockwise direction. And FT will create this is anti-clockwise position. So you need to balance this all this moment together. Okay, we move forward. So we start with the F resultant equal to PC or P. No, just now I mentioned gauge, right? It's not gauge. It's a pressure through centroid times the area. So in this case, we convert our pressure with P0 plus rho GH through the centroid, okay, times A. And because we are given specific weight gamma in the question. So in the question, in the diagram that you see is 9.807 kilonewton. So you substitute your rho G equal to 9.8 or gamma or the specific weight. Yeah. Centroid is always half. Right? You take the length, divide by half. Here, this is your centroid. So you take L divided by 2, you get your centroid. Then your Y prime is a governing equation. Y prime equal to Y over centroid plus rho G sine theta, your second moment of area, divided by FR. Again, there's appendix inside the Moodle. You need to download it and have a look in it. Yeah. So what I need to highlight is your second moment of area. You use BL cube divided by 12. Yeah, BL cube divided by 12. Why? Because this is a rectangular shape. So when you have a rectangular shape, your IXX will be BL cube divided by 12. Again, as a reminder, go appendix and download the appendix file on second moment of area. Yeah. Go and find this information. So in exam, the formula won't be given anymore. It will be online exam. So we expect you to know how to find IXX. Yeah. So in exam, you need to write out the formula for your IXX. So BL cube divided by 12. And again, your centroid is half of your length here. Your length. Your centroid is here. So this is your length of your what LC or YC also can. Yeah. So you replace your YC with the L divided by 2. And rho G sine theta is your uh, rho G sine component is your specific weight. Yeah, this one is your specific weight component. And your FR, you replace the equation into this one. Okay, let me see. Yeah, okay. Then area is B times L. B times L. B is the 2 meter. Right? You are given the length and height of the door. You have 3 times 2 uh, dimension for the door. So this one you need to look back at the question itself, right? So area is B times L, so 2 times the L. Then you simplify the equation, right? Simplify the equation, then you can take out the B, take out the L accordingly. So at the end, your Y prime equal to L divided by 2 plus your specific weight, L2 divided by 12 divided by pressure plus specific weight again, L divided by 2. Okay. So at the moment, we still deal with a general equation. We tidy up all the equation we need to use. The next, we just substitute all the value inside there. Okay. The next one, we're going to focus on moment. Okay. So moment in A, again, AZ and AY doesn't create anything because we focus on A. You only have FR and FT on the point A. So we have an equilibrium equation with us. So all the moment at point A equal to 0. So we can write this equation. We assume anticlockwise is positive. Anticlockwise moment is positive. So Ft times L, you get the first moment because of Ft. You get the first moment because of Ft times L. You get anticlockwise moment. And then second one is clockwise direction. So you have a negative here. Fr times the length of this one. So how you get this one? You take the L minus Y prime. So you get the second moment. Any questions so far? Any one of you want to ask me a question? Or any one of you don't understand?
No, sir. Clear.
Can, eh?
Clear. Yeah.
Okay, good. Cool, you okay?
Yes, sir.
Okay. Right. Then you rearrange the equation. You get this equation like you see on the screen. And then the rest is just substitution. Yeah. There's no complex concept here. Just a rearrange your equation, or you can stop at the third line here and then you substitute. Yeah. The next is just to tidy up. Yeah. So we have our FR, we have our Y prime location, we have our YT also. So in exam, you can calculate one number, and then you substitute into the equation here. So what we're doing here is we write everything in the equation. We substitute our FR here, and we substitute our Y prime here. So it's going to be a very big equation. So if you are not good in summarizing equation, You can go ahead and calculate the number first, right? And then you substitute inside here, right? So let's say you get FR equal to 1, Y prime equal to 2. Then when you substitute here, you need to write this equation, and then in your answer, you write 1 minus 2 divided by L. Let's substitute the L also. Okay. All right. So you're able to get the final answer for the FT. Yeah. So in my slide, I won't do the substitution numbers for you. I know all of you know how to substitute number and use your calculator. So important is you understand the concept that we use. Okay. So the concept we use for this example, again, we are used back the governing equation. We use the centroid pressure. We use the y prime equal to yc plus rho g sine theta ixx. And another one is maybe a hidden equation, but we expect you to know once you develop your free body diagram. You have a force and a distance, then always remind yourself the question is trying to ask you the moment, yeah, the moment along A. And of course, in exam, we will try to guide you through the answer that we're looking for. There will be a section I ask you to calculate the moment at, for example, calculate or analyze the moment at point A. So you do a calculation for point A. You put all the moment at point equal to 0. Then the rest is just application of all the substitution and rearrangement of equation, and the next one is your answer. Okay. Any question so far?
But I can't see the slide.
You can't see slide.
Yeah.
How about Amir and
Can see so.
Ken?
Yeah,
Now,
Who
now,
now? Okay, all right. So you need to check your connection. Okay, we move forward. Right, move forward. Now we reach the end of your chapter 2. Okay, and again, your test 1 will cover up to chapter 2. Yeah. So the next we're going to look at buoyancy. Yeah, buoyancy. So buoyancy is a force that make a body to float. So the definition or the line that you see on the screen here is a textbook definition. So it's a net vertical force acting on it due to liquid pressure. We call it buoyancy. Yeah. So if you try to immerse a object in a water, and then if the object will float, then there is a buoyancy. So the word buoyancy means floating, a floating force. So if you see a diagram on the screen now, you will see that we have a cylinder that go into the water, and once you go inside the water, remember the body will experience pressure, and the pressure is acting on all the direction on the body. And then if the object doesn't move or stationary, means that it already reached equilibrium, meaning the force acting on the body is balanced, and there is a force that make the object floating in that particular position. So in this diagram, you'll see that there's a H1 here, there's a H2 here, and the density is given, and you see an inverted triangular to represent the ambient pressure. And we have dV hat means is the volume that displaced by this body, or you can say that it's a this cylinder body, and we have a A here. Yeah, dA is the area over here. Okay. Then we try to develop the equation. Again, the concept is just to balance all the force equal to 0. So again, call back once you have an object and you are studying about hydrostatic pressure or hydrostatic force, then or something in the water, always call out P equal to P0 plus rho GH. P0 is ambient pressure. Rho GH is here. Rho GH is the pressure that acting on the body underwater. So net force, if I show you on the screen here, is quite self-explainable. The axis that we have here, is Z positive going up. So we will have pressure acting on point number 2 here. It will be, okay, pressure at point number 2 will be pressure, ambient pressure plus rho GH again, and the H is number 2. Okay, and then you convert this force into this pressure into force number 2. Then you do for the top one. So pressure acting on point number 1 here or top here will be again ambient pressure plus rho GH also. Rho GH, and the H here is H1. So what you do is you balance the force, and again you convert the P1 into F1. So you convert, when you convert, just times the area that you have. So the first one, you focus on the surface under there, point number 2 minus point number 1 or surface number 1, then you get the net force acting on the object. So you might ask why we don't need to consider the body, because the body doesn't do anything. Yeah. Yes, there is a force acting on the body here, but the force is balanced. The force is quite balanced, so we don't need to calculate the force on the horizontal axis here. And again, just back to the definition of buoyancy, is we are interested in the net vertical force. Yeah, we talk about buoyancy, or if you see the question asks you to calculate buoyancy force acting on the object, it means you only consider the vertical component. Okay, so these are all the hints or the keywords for you to focus on. And then the rest, you just simply simplify the equation. From here, you simplify you take out the P0, right? P0 here, and then you factor out all the common factor. So you only have the differences of H2 minus H1, which is the difference of height here. So you will have rho G dV. dV is the volume. dV is the volume. You take area times the H here, you get the volume that dispensed by the object. Or maybe in earlier years, you learn about Archimedes' principle. Yeah. So buoyancy force also proven by Archimedes. The next one is just integration of what we have. So if you integrate something with the small forces on the body, then you get a total force acting on the body, or the buoyancy force acting on the body. This is just a mathematic presentation. Okay. Yeah. Okay, nothing complex here. Or rho GV equal to buoyancy. I'm going to see one example on the application. Okay, so yeah, this is quite straightforward. Right? Rho GV, you can see that is the buoyancy force equal to weight of the displaced force. Right. So we can say we can use rho GV or volume, rho G volume to calculate the buoyancy force. Quite straightforward. Okay. We look at one example. So let's say we have a balloon. So and you assume that this balloon is taking a shape of sphere with a diameter of 15 meter, and we have a load of 600 Newton in the basket. So at what atmosphere temperature must the air be heated in order to achieve a lift off? So your air is at standard temperature and pressure. So this solution is to apply the buoyancy force, the buoyancy equation. Okay, buoyancy equation is quite simple. It is rho G times the volume displaced. And we will need to have a free body diagram to explain the equivalent of forces acting on the body. So again, apply all the vertical force equal to 0. In this case, you can write as because the axis was not given in the question. So when you answer this kind of question, you can give yourself a free vertical. You can use Z, you can use Y for vertical. In this case, we will apply ideal gas equation that you learned in your thermal 1. Right. So again, recall buoyancy force, rho GV, all the force in Y direction or vertical direction equal to 0. And ideal gas equation will be pressure equal to rho RT. Pressure equal to rho RT. This is what you learn in the thermal. Okay, so we have ideal gas. We will consider atmospheric pressure throughout. So all the force in Y direction will be equal to buoyancy force. Let's see if I include the free body diagram. Oh, there's no free body diagram. Okay, so if you draw a free body diagram, we assume that this one has a sphere. So we have a load, W load. And then we have a buoyancy force, FB. And we have hot air also. Yeah. So hot air will W hot air. Okay. Because we know that all the air have mass and gravity will pull down the air also. Although we do not feel it, but there is a gravitational effect. Okay. So we apply the buoyancy force equation. Force buoyancy given by rho ATM GH, and then the hot air, rho GV also, but the rho we use for hot air. For the first term here, the F buoyancy we refer to the air at atmospheric, and then minus the load that we have inside the basket equal to 0. Then we substitute. Okay, so again, how you know the value of rho for hot air? You need to use the appendix data. In appendix, there's atmospheric data for air. So at a certain temperature, then or certain altitude, then you get a certain parameter. So we rearrange the equation above. Then we get rho hot air equal to rho ATM minus the load that we have divided by GV. The next is just application of your mathematics. So rho ATM is 1.225 kilogram per meter cube minus the load will be see here, load will be 600. Oh, so the load is 600, but when you calculate the velocity, the volume, the sphere volume equation, you need to go and find out. So when you rearrange the equation, you will see 6 above the equation. It's talking about the sphere volume here. All right. Then at the end, you arrive at the rho A, kilogram over meter cube. Okay, again, you assume you already know how to calculate the sphere volume, yeah? So if you don't know, you just Google, right? How to find what is the equation of sphere. So in exam, you write out the equation for volume the sphere, will also get you 3 marks there. Huh? There's a 1 mark for additional information. Okay, the next one, once you get the rho hot air, you do a comparison by using ideal gas equation. So you know that P equal to rho RT. So if you compare pressure 1 and pressure 2, you can get the same parameter, yeah. So on the left hand side, you focus on hot air. Okay, P equal to rho RT. If you move the P to left hand side, you'll get a constant value. Rho RT divided by P. So all the if you work in ideal gas, you can compare 2 different gas with a constant value like right on the screen here. All right, so that's why we can use this equation. Yeah. So, or you can invert it also. P divided by rho RT, also a constant value. So both give you a same constant value. So we can directly give a comparison. So we have P hot air divided by rho hot air RT hot air. And again, when you use the temperature here, you need to be careful on the R that you use. The R is the gas constant value that sometimes if you refer to a standard chart, it was in a Kelvin. It's in a Kelvin, it's not Celsius, in a Kelvin. So at the end, when you calculate your answer will arrive at Kelvin. Right? So just be careful on the notation here. Here, our atmospheric pressure will be the same as the pressure of our hot air. So we can cancel these two. Then you rearrange for temperature of your hot air divided by the ratio of your rho ATM divided by rho hot air. Then at the end, you can arrive at hot air here. Now in this case, because you cancel out the constant value here, so by having the standard atmospheric pressure temperature, you're able to find. So if you refer to appendix, yeah. So again, if you refer to appendix, you're able to know what is the standard temperature for air. So for standard case, is 15 degrees C. Standard pressure will be the atmospheric pressure that's stated in the table. So you need to go and look at appendix A. Yeah. So at the end, you arrive at the answer. Any questions so far for this example?
No, sir.
All right.
No, sir.
Okay. So this example is on air. So the next one, maybe in your test or exam, it will be in water. So the concept still same. You apply the free body diagram and then call out the governing equation of the buoyancy. Then you solve the problems. The next one is on stability. So the word stability itself is CG, that like the one that you see on the screen here. So if your CG is shifted, then you make the body or the vessel to become unstable. So if the object is in the water, there is no stability problems. If the object is in the water, then you only have buoyancy problems. Right? It float in the middle of the liquid, then you have buoyancy problems. If you have hydrostatic problems, then the object will be slanted at a certain degree. Yeah. Hydrostatic will be rho GH or P0 plus rho GH, depends on the question itself. But when you talk about stability, it will link up with your center of gravity. Yeah. So if you're given a object like you see on the second diagram here on the left hand side, so why the diagram say is stable? Because if you see the vessel is tilted to the, it's a clockwise tilted, right? So I mean the body is going, if you in the boat, it is a bit heavy on the right hand side, so it was slanted to the right. So you want to balance this vessel, you need to have a counter moment to shift back the position. So if your buoyancy force is going up like that, and your gravity is going down like that, so the body will be stabilized to make the body to stay in this position. Okay, to stay in this position. It will be like the same case as the straight vessel like that. So if your CG go down, this is your CG effect. So if your object go like that, to stable like that, your buoyancy force is aligned with your CG line. Yeah. So this is your buoyancy force. So CG go down, which is your mg, your weight go down. Yeah. So your mg will equal to your buoyancy force. So it will stay in this position, stable. So you look at the second diagram. So second diagram, the body was slanted to the right, and then the buoyancy force is going up like that, and the gravity is going down like that. So you will see that there's an imbalance of forces here. The balance is imbalanced because of the CG position. Yeah. And yeah, remind that why the floating vessels we can use buoyancy, because the equation of rho GV is also equal to the volume displaced by the vessel. So the volume displaced by the vessel, or the one that go inside the water, is the volume times the rho G, will result the buoyancy force. Okay. In short, it's just that be careful on the location of the CG and the line of action of the buoyancy force that determine the stability. So yeah, so this explain, but nothing complex here. CG will be about mass. then I will show you one YouTube video. Okay, so you'll see this is the modern ship stabilization. Let's see. You're able to see my screen on the YouTube, right?
Yes, sir.
Okay.
Yes, sir.
Yes,
So I open up my YouTube. So it's a called active stabilization system. So on the left here, you see a ship with a ballast system that it can go up and right, up and down for left and right. And then this one is without the stabilization. So if in the modern ship, then you have an active system like this. So you see how the system works. So if the ship try to yaw to the left, the system will fill up the water. It used the concept of Archimedes or buoyancy force also. So you see the difference between the two. This is how the active stabilization works. This one is the roll compensation. Okay. Now, roll compensation means this one is in another dimension. Just now you see in 2D. Now you see a little bit isometric view. So you see that the system control the water go inside the other one. Pitch compensation means is go up and down the nose. You see the pump in front the ship here. It will pump water right to the front so that there is a buoyancy force in front. Okay. With this, we conclude our chapter 2. Okay, let me stop the recording.